Hey everyone. So just as Spider-Man realized that his powers come with responsibilities and obligations, we in the AI community are realizing that our innovations are comes with the same. And that's what we're going to talk about today. How we can build AI but responsibly. But why do we need to be responsible? Because if we don't be responsible, incidents like this will continue happening. Earlier this year, Anthropic, the creator of the chatbot Claude, had a major security breach. Their users got their information leaked. I'm talking about sensitive information like account details, financial details, and that's a very bad problem because if that information falls in the wrong hand, they can cause a lot of harm to the users. And that's a problem we need to solve. And only one way we can solve this if we build AI privately. And this is not a opinion held by a small amount of people. Studies have shown that more than 57% of the AI consumers believe that AI pose massive security risk to their information. We will never be able to scale of our AI innovations without incorporating privacy in it. And that's what we do at Bagel. So Bagel is a machine learning and cryptography research lab, and we are focusing on privacy-preserving machine learning. And I'm Bidhan. I'm the founder of Bagel. Previously, I used to be the AI/ML infra lead for Amazon Alexa, one of the biggest machine learning systems that exists on this planet. We believe that the North Star for AI is both decentralized and private. And when I say private, I mean private at every step, from the data to the compute to the models. Because if there's a leak at any stage, it can cause catastrophic consequences for the consumers. And one of the best ways to do that is fully homomorphic encryption. Homomorphic encryption is practically the digital equivalent of invisible ink. It can encrypt the data end to end, and an application can perform arbitrary computation over it without ever getting access to the unencrypted raw data. How does it work? The concept is very simple. So when you encrypt any data, usually without homomorphic encryption, it becomes gibberish. You cannot really see what's going on. The data doesn't really make sense to you, or the applications are building on top of it. But when you do it encrypted homomorphically, you can do all kind of computation on top of it. The stage we're at today, you can usually do just arithmetic computations, but we're getting to a stage where we can do other types of computations as well. So let's focus on the artificial intelligence use cases of homomorphic encryption. How can you do machine learning inference on AI models with data which is fully homomorphically encrypted? Usually, it's a process between a data owner and a model owner. And here in the diagram, you can see that there's a neural network. Neural network is a type of AI model. So the data owner encrypts the data using homomorphic encryption. And then it sends the data to the model owner. The model owner should have some kind of knowledge, what kind of scheme was used to encrypt the data. And then they would be able to do the computations over the data without ever having access to it. And then the data model owner will send back the result of the inference back to the data owner. And the whole thing happens exposing the data to the neural network. And then when the data owner gets the result back, they can decrypt it with their private key, and they will have the raw result they desired all along. There are some challenges with these kind of approaches. As I mentioned already, that you can only do arithmetic computations on fully homomorphically encrypted data. And when you go into neural networks, it's like a very complicated AI model. In that, you have non-arithmetic computations as well. Like you can do like greater than, less than, those kind of things. And how can you replicate that using homomorphic encryptions? There are clever ways. Without going too technical, you can do low-level polynomial approximations of the non-arithmetic computations within the neural network. And that will give you quite accurate result of doing the computations using FHE. Now let's talk about training of models. So if you're wondering, like inference happens after you make the models, and training is how you create the models. And you can create and train the models using FHE as well. We at Bagel have achieved that internally too. We have trained small linear regressions, and which we are using internally for different use cases. And how does that work? I'll tell you guys first how the model training works without an encryption. There's a data owner, and there's a model, the neural network, which is not trained yet. So the data owner sends the data to the neural network, and the neural network owner does some computations on the data so that the model learns whatever is in the data. So if you want the model to learn about all the 5,000 side events of ETHCC, it will learn about it, and it will be able to give you really intelligent information on those sample data. But what if you don't own the model yourself? What if it's a decentralized network where I have the data and some unknown person has the model, and I want to use my data to train the model and get some results back from that? How can I do that? And the data I have might not be some public information like ETHCC side events. It can be really personal information, like my medical records or my financial details. How can I train a neural network which is held by some other party who I don't trust using my private data? That's where homomorphic encryption comes in as well. So what I can do is encrypt the data with homomorphic encryption, and usually there's a public key and private key of the encryption set. And then I send the data and the private key to the model owner. And I'll also have to tell the model owner what kind of encryption scheme I used to encrypt the data. And the model owner would be able to perform all the computations they need to train the model using just the encrypted data and the public key information. And then they will have some result of the training. They are called weights and parameters. And they will send the results back. And the beauty of the whole thing is that when you generate the weights from this neural network, which did the computation over encrypted data, the weights generate in an encrypted form as well by default. You don't need to encrypt them in any way. So then even the neural network owner never sees the weights because it generates in an encrypted fashion by default. And it sends it back to the data owner. And now, if I'm the data owner, I have my private key, I can decrypt it however I want, and I have the unencrypted weights. Totally untrusted parties interacting with each other without ever revealing their private information. As I mentioned, we are a deep research lab who has been researching this space for a while. We are one of the leaders in privacy-preserving machine learning. We work with FHE, we work with other privacy-preserving technologies, and we're bringing them to the AI space. And we share our research on our blog. I encourage everyone to check it out. Our approach to our blog is technical journalism. We publish our research in an unbiased way from raw experiences we get while experimenting. So as I was talking about, what is the North Star for AI? The North Star for AI is both decentralized and private. There is no other way. We cannot have centralized AI because AI is one of the major paradigm shifting technology in the history of our species. And we don't want any centralized entity to control that. But this decentralization will not scale if the privacy-preserving AI doesn't happen. Well, that's the end of it. And yeah, thank you for following along.